In this conversion problem, there's a lot to consider. So remember, as we get started to do this problem, remember those three parts. We have to find sort of a starting point, an extent, how much sort of standalone value. Two, we need to identify conversion factors, ratios, that'll be used as boxcars along the way as we build from the engine through those boxcars to the final answer. And we have to identify what is they want to know. And we put that at the end. So let's do that as we read this. I'll highlight and mark what might be at different places. Hot summer night, two kids, they drag a 10-pound bag of ice. And right there, there's a standalone sort of number, 10 pounds of ice. They drag it into a tent and try to cool the air down. Disregarding humidity, body heat, insulation, and all that, they determine that the temperature, we can determine the temperature drop that might occur. So that's kind of our goal, is to figure out what the temperature drop is. So kind of remember, I'm going to be putting some sort of unit over here that I think is going to represent that temperature drop. We'll assume the tent has a volume of 2,565 cubic inches, which is a pretty small tent, but anyway, that's a standalone value. It doesn't seem to have a per something, like this per that. As the air has a heat capacity near, now not specific heat capacity, that's always in joules per gram per Celsius, but this is saying it takes this many joules to heat up 1 liter of that air in the tent, I guess, or air in general, 1 degree Kelvin. So that's actually a conversion factor. We can recognize it as such. So I'm going to box it in. I'm going to make a little, say that's my first possible boxcar used in the dimensional analysis. So I boxed that in. What ice, so this is for ice, has a heat of fusion of 333.55 joules per gram. So there we go again. We're going to box that baby in because that is a possible conversion factor used in our dimensional analysis. And we have two others to just look to be describing anything that has a mass. It has a mass. We can talk about it in grams or in pounds, and if it's in volume, we can describe it in liters. And there's a conversion factor given here just for cubic inches. So these are just sort of standard conversion factors. Can talk about any particular application, ice or air or whatever. All right, so I think we're ready to start. And so I think just looking at this, maybe what we could say is that the ice is really what's going to drive the driver or engine for temperature drop. So I'm going to put that over on the very left side of my box. And I'm just going to put ice here just to, just that we keep a track of what is it we're representing here as 10 pounds. It's 10 pounds of ice. So I've already used that one. I'm just going to start. And now, again, I may want to have over here, it says the temperature drop. So it has to be some sort of unit for temperature. And as you look at all of these, the only one that comes into play is this joules per liter. And sometimes it should be maybe seen as liter dot Kelvin. Looks like we're looking for, it's going to put uncertain, some sort of value in terms of Kelvin. We want to know what that temperature drop is in terms of Kelvin. You say, well, how'd you know that? Because there's no Celsius values anywhere here. There is, though, a Kelvin value. So there we go. All right, so we've got our starting point, we've got our end. Let's connect them through the boxcars. And we'll tag them as number 4 here, 3, 2, and this will be 1 boxcar. So our numbered boxcars. Well, right out of the gate, we have pounds, LBs. So we're looking for something that has pounds. That doesn't have it. This does. That doesn't. And this doesn't. So you know what? We're kind of limited to bringing car number 3, come on down. And it's kind of 1 LB on the bottom is equal to 453.6 grams. Next boxcar has to involve grams. So no, yes. We've already used number 3, so let's take him out. And that doesn't, so there's nobody else that has grams except this one. And this is talking about anything, but this is really about the ice now that we're starting to talk about. It says, hey, and that's really what we were talking about already. This can be applied to ice. It can have so many pounds, but it can also be written in terms of grams. So we're just continuing this discussion of ice to this fusion value, the heat it takes to, or the heat given, it takes in as it goes from ice to water, this heat of fusion. So we can say the 300, oh, got the wrong one. The 333.55 has to go on top. Why? Because grams has to go on the bottom to cancel with grams on the top of the conversion car 3. So we're bringing conversion car number 2 down, and it's 333.55 joules per gram. Moving on to the next box car. So 2's done, 3 is done. We have joules. Now this has all been about the ice, but there is a joule term here that talks about the air, and yeah, the ice is going to be taking heat from the air, so there's a relationship that we're going to start to kind of cross over. We're going to start talking about the air. We need a transition because this temperature drop is of the air in the tent. So this is a good one to use. We're going to put 1.216 joules, has to be on the bottom. So we had to flip this one because the joules is on the top here. It has to be on the bottom in the next conversion car over 1 liter. And I'll put a dot there just so we know it's not one unit, L and K together. It's 1 unit of L, liter, and 1 unit of Kelvin for temperature. Now we're moving on. So we've gotten rid of 3 box cars. Number 1 has been used. 4 looks like it's going to be used the next spot here because in the end, I don't want anything other than Kelvin, and getting liters out will certainly help. So I can put 0.0164 liters on the bottom, again, because it's having to cancel with that liters, and have just 1 inch cubed on top. But notice something here. I don't want the inches cubed either. So this value right here that sort of stood alone, the volume of a tent, we can put it just with a 1, or you can write in there tent if you wanted to, but 1 will work. We can say I needed to get rid of that inches cubed. This is the volume of 1 tent, like Stuart Little's tent, because it's like 100 inches by 100 inches by 100 inches or something. Not even that, it's like 10, 10, 10. It's a really small tent because this value really should be like 900,000 instead of 2,000. But anyway, that said, we can go ahead and cancel now all those terms that we don't want, those units, and just check yourself before you do the math. This cancels the inches, that gets out of there. The liters is gone, the joules is gone, the grams is gone, the pounds is gone. And so you can kind of check yourself before you do the math that, hey, yeah, the only standing unit is Kelvin. So this will work. I'll multiply everything on top, 10 times 453 times 333.55, hit equals. Then divide it by 1.216, hit equals. Divide by 0.0164, hit equals. And divide by 2,565, hit equals. And you'll get something around 29,000. And you'll say, what the heck? That can't be the temperature drop. And you are right. 3 things before we just shut this thing down. 1, that's way too small. Stuart Little lives in that tent, about 900,000. So that might bring it back to like 290 or 100. Second, we don't factor in that air doesn't take up a lot of heat, but your body in the tent with sleeping bags and everything would take up a lot of heat. Third, you can't go past 32 degrees Celsius, or the ice will just go back to ice. So you can't keep on dropping. The ice will stop giving off heat, or sorry, stop taking in heat, because it's dropped below freezing point. So that's kind of cool to think about what really in application would happen if your ice starts to take in heat. It can only go to the point at which ice freezes, because then it won't melt anymore. Thanks. Bye-bye.